Great. Well, thank you very much for the invitation. It's a super interesting workshop, and I'm very glad to be here. So I would like to present a talk on a recent preprint on the classical boundaries of quantum supremacy. This is work that was done with Alexander Zlokapa from Caltech. He's an undergraduate student there, about to graduate, and Sergio Boixo from Google, who was one of the principal co-authors of Google's quantum supremacy work. So speaking of the quantum supremacy work, this is the paper that I'm pretty sure everyone attending here has seen and possibly even read. The demonstration of quantum supremacy using Google's Sycamore quantum chip. It's been a remarkably well-received work with, which has generated a tremendous amount of interest. I think it's been cited about as much as the discovery of gravitational waves in its first years, and indeed it is an outstanding breakthrough. And I'd like to devote this talk to discussing what it means from a computational perspective. So what was actually done? I'll get into that in much more detail later, but basically the classical intractability barrier was broken using their chip. They performed a calculation on a 53 qubit chip in 200 seconds that no current classical computer can perform faster. And this was done despite the presence of decoherence and without any assistance from quantum error correction. If anything, it is certainly an interesting example of an open quantum many-body system, which is why I thought this would be an interesting topic for this workshop. The work does raise a lot of questions, and here are some of the questions that I'd like to ask and start to answer in this talk. So will the quantum advantage that was demonstrated continue to hold if we were to scale the same chip to larger circuits, that is more qubits and larger depth? Or is it actually the case that classical computing takes over if you were to do that? And if classical computing does become supreme at larger sizes, then what are the circuit sizes at which this transition to classical supremacy would happen? How does this depend on the error rates? What is the right error model? And if we knew the right error model, could we even simulate it? So as a preview to the conclusion of this talk, this is in essence the diagram that summarizes our results. It shows regions of classical advantage shaded in color in a diagram that is the circuit depth versus the circuit width. Circuit depth is how many gates you apply. Circuit width is how many qubits you have in the circuit. The red dots are Google's results, and you see that they protrude into the white region, which is where there is a quantum advantage. Also shown are contours of computation time. This is the quantum computation time. And you can also infer from here, therefore, that if you were to try to go to larger circuits, very quickly the quantum computation time would increase dramatically. And I'll talk about why that happens. Okay, so that's the context for this talk. Now, let me tell you a little bit about the type of circuits that Google used to demonstrate quantum supremacy. These are random circuits. And here's a schematic, it's a figure taken from their paper of what these circuits look like. So here's a unit cell from the Sycamore chip. The qubits are the X's. The gates are numbered with the letters here. And a random circuit it's not a completely random circuit. It's random in the sense that we pick random single qubit gates from this set of three, the Pauli X, Pauli Y, or the W gate, which the choice of which is random, and each one of these is applied to a qubit in a given cycle. And then within that cycle, each single qubit gate is followed by one 2-qubit gate. And the 2-qubit gate is an I swap. So this is the type of 2-qubit gate that is. And there are patterns of these I swaps that are being applied. There are so-called, or these are entanglement patterns, if you'd like, because they generate entanglement in the circuit. There are what they call the intractable, that's classically intractable patterns like ABCD, CDAB. And it turns out there are also simulable, that is more easily classically simulable patterns like EFGH, EFGH. So I'm not going to go into the details here, but I want to point out that there are different ways that you can run the circuit. Again, the randomness comes from the single qubit gates, and I think there's a strong connection here to some of the quantum chaos results that we heard about from Thomas Prosen yesterday. So it's possibly an interesting connection to try to make within this workshop. Now, suppose you run a random circuit like this. What's the task? The task is random circuit sampling, RCS. And what you need to do is to sample from the probability distribution of outcomes generated by a random circuit like this, where the input is the all zero string, and the output is some bit string X that you measure at the end of each run of a circuit. In other words, you need to generate a bit string X with the right probability. Is this problem classically hard, you might ask? And the answer is yes, it is known to be classically hard for sure for noiseless circuits. In fact, the average case can be proven to be Sharpie hard. Although that's not, the hardness is not the case for shallow depth circuits, where shallow means that the circuit depth scales like the log of the circuit width. But of course, the reality is that we can't run these ideal circuits. We run a noisy version, which you might think of as being described by some CP map, E sub u, with a fidelity f. So with probability 1 minus f, you, in this depolarization model, you apply the identity operation, and with probability f, you actually succeed in applying the ideal unitary that you meant to apply. So instead of sampling from the ideal expression up here, you actually sample from the distribution generated by the CP map. Now, clearly, if you accept this depolarization model, in the high noise limit, where f is close to 0, you get a uniform distribution. And uniform distribution, of course, would not be hard to simulate classically. So it's clear that the random circuit sampling task, the hardness thereof depends strongly on the fidelity f. But in fact, it's conjectured, and it seems plausible, that for any constant f greater than 0, this problem is already classically hard. So it's all about trying to generate sufficiently large f in some sense. And Google chose to quantify the hardness of these circuits using a fidelity measure that they call the linear cross-entropy benchmarking, which I've defined here. So what is this expression? X is just a bit string, so we're summing over all possible bit strings of n qubits, 2 to the n of them. P is the probability of bit string X that you pre-compute classically and exactly for the ideal circuit. Q is the experimental probability of bit string X that you would get by running your quantum circuit in its noisy version. And the meaning of this fidelity is that it really is like a regular fidelity. You can show that essentially it corresponds to the probability that no error has occurred while running the circuit. You can prove that for a perfectly implemented circuit, this quantity is 1. And it's obvious that for a totally noisy implementation, when you sample from the uniform distribution, it's 0, because if you take Q to be 1 over 2 to the n, the uniform distribution, then you immediately get that this evaluates to 0. Now, in reality, you don't have access to the exact distribution Q sub u. So what was done was to run the circuit many times, n sub s times, the number of samples. And every time you run the circuit, you get some bit string, x sub I, which you then plug into the pre-computed classical probability, and you evaluate this expression. So this is the quantity that was actually computed. Okay, so when this was done in Google's experiment, at the largest circuit size of 53 qubits and 20 cycles, the depth is 2 times the number of cycles, so this is depth 40. What they found was a fidelity that is about 10 to the minus 3, and this was done by collecting 1 million bit strings in 200 seconds. Now, in the paper, they estimated that it would take the world's most powerful classical computer, Summit, 10,000 years to generate the same number of bit strings with the same fidelity. And that claim of 10,000 years generated some controversy, and there was a quick succession of papers that showed that actually that was probably too long, and that time has since been reduced to a matter of a few days. But it has not so far been reduced below 200 seconds. So the fact that there is no classical way to compute this fidelity below 200 seconds is essentially the supremacy claim, and it still stands. Now, I want to point out that the relation between the numbers here, 10 to the minus 3 and 10 to the 6, is not an accident, and we'll talk about that in a bit in more detail. But first, how does the fidelity scale with the width and the depth? So this is a busy graph from...
Can I quickly ask maybe,
yes,
was
please.
it reduced theoretically or an actual run on a supercomputer?
This?
Yeah.
Yeah, these are the experimental results.
No, but the claim that it can be done in a few days or so, was it done on an actual run or?
Yes, the last paper from the group from China actually calculated these fidelities on their own machines, which are similar to Summit.
Okay, thanks.
So this plot is from the Google paper itself. It has too much information for me to get into, but what I want to convey is that the fidelity decays exponentially. So notice that this is a log scale versus the number of qubits of the fidelity. And on the left here, what they did was fix the number of cycles to 14 and increase the number of qubits and compute the fidelity for a variety of different types of circuits and the so-called simulable pattern. On the right, they fixed the number of qubits at 53, and they increased the number of cycles for the hard pattern. And again, the point here is not to go into the details of exactly what everything means, but rather I just want you to take away from this that the fidelity decays exponentially, and that's going to play an important role. Now, I've spoken for a while about what Google did, but if you're confused about what exactly the computational task is, then that's okay, because so far it's not exactly clear, in fact, what the computational task is. So let me try to define it. It's the following. The task, which in our paper we called XCB for linear cross-entropy benchmarking, is to generate a sample of n sub s bit strings such that you can confidently estimate the random variable f. In other words, you have to be able to estimate it to within a standard deviation sigma that is less than itself. Otherwise, it's a meaningless estimate. So this is the task. You need to generate enough samples such that you get the standard deviation to be low enough. And then if you can do that faster than can be done on the best classical hardware, on your quantum hardware, then you can declare quantum supremacy. Now, with this definition, we can immediately figure out how many samples are needed. So by the central limit theorem, the standard deviation will go like 1 over the square root of the number of samples. And by simply equating sigma and f, you can back out that the required number of samples scales like 1 over the fidelity squared. So this explains the comment I made earlier that they needed 1 million samples given the fidelity that was measured of 10 to the minus 3. Okay, so clearly because the computation time is proportional to the number of samples needed, each sample is 1 run of your circuit, that determines the quantum time scaling. And now, in order to make progress, we need a model for this fidelity, which we can extract empirically from this data. So here's a formula that I'll explain on the next slide, which is an empirical fit to the fidelity data presented in Google's paper. And so this single expression collapses both of these graphs, or rather fits both of these graphs with parameters, two fitting parameters, lambda and gamma, whose meaning I'll explain. But here's the visual of how good the fit is. It's okay. So this graph on the right is exactly the same data as the two graphs on the left, just presented jointly. Right, so the red crosses are what happens when you fix the number of qubits at 53 and you increase the number of cycles. And the blue data is fixed number of cycles as a function of the number of qubits. And so here, the red data, the fit is really good. The blue data, the fit is not as good. And that's, I think, actually an interesting problem to figure out how to get a better error model. Okay, so where is this formula coming from? Why does it work? It comes from an extremely simple stochastic Markovian error model for the fidelity decay. So let's say that we have a gate set G with gate errors E sub G and a qubit set Q with qubit errors E sub Q. The simplest expression you can imagine is to just write the fidelity as the product over the qubit infidelities times the gate infidelities, like so. Fidelities, I mean, not infidelities, right? So the infidelities are the errors. So this is the fidelity, product of fidelities of the qubits times the product of fidelities of the gates. And then we can approximate this as follows. For each cycle, we have n single qubit gates, and you can count, you need n minus root n over two qubit gates due to the tiling pattern that they used on a planar architecture. So if you multiply m cycles by n 1 qubit gates and n minus root n 2 over 2 qubit gates, you get a total like this. And that is the expression you see here, with one fit parameter lambda, which we now interpret as the gate error rate. And the qubit errors, the second part of this expression, well, the qubit errors scale as a function of n, and they scale as n, because for every qubit you have a state preparation and dominantly a readout error. And so another fit parameter is gamma here, which turns out to be about 10 times larger than the gate error rate. So that's the extremely simple derivation of this expression for the fidelity. And one of the questions I'd like to pose to the workshop participants or challenges is to come up with a much more sophisticated and better error model. I think that's a really interesting problem. Okay, so now let's discuss the implications of all this. If you want an expression for the quantum runtime, well, it obviously scales with the number of cycles. The more cycles, the longer you have to run your circuit for. And also scales with the number of samples that you have to collect. Right? And so since we know now that the number of samples scales like 1 over the fidelity squared by the central limit argument, and we have a model for the fidelity, we can plug that in, and that's the expression from the previous slide, just with squared. Okay, so this is the quantum runtime, which we would like to compare to classical algorithms in order to establish whether quantum supremacy continues or whether it will lose to classical algorithms. So, of course, there's an infinite choice of classical algorithms here, and I'll focus on a few that have been analyzed in the literature already. So what I'm about to say is not original. This is borrowed from other people's work. Let's start with the classical Schrodinger algorithm. So this is an algorithm that is a completely brute force. Basically, it just solves the Schrodinger equation, if you'd like, for the circuit. So it provides a fidelity 1 full circuit simulation once you finish running the algorithm for a given randomly generated circuit, you could just repeatedly sample from the amplitudes that you've computed, and you can use that to solve XCB. So how does this brute force algorithm scale? Well, it scales like m times n times 2 to the n, and you shouldn't be surprised by the 2 to the n, of course. So if we compare that to the quantum expression, you just divide them, you get this factor here. And the factor of m in the exponential, which shows up in the quantum case, but not in the Schrodinger algorithm case, means that the Schrodinger algorithm is going to beat the quantum algorithm at fixed n for any m larger than some threshold depth, which you can back out from here. So this is what you get for the threshold depth. And at 53 qubits, you find that the Schrodinger algorithm is going to win for any circuit whose depth, or whose the number of cycles rather, is 87 or higher. And in fact, if you take the limit, it happens already at a number of cycles equal to 71. Any m larger than that, Schrodinger wins. The Schrodinger algorithm wins. So that's one algorithm, which is very good for small n and arbitrarily large m. There's another algorithm which is kind of the opposite limit. It's an algorithm that's appropriate for shallow depth simulation. It's due to Bravi, Gossett, and Movasag. And it scales like n times 2 to the m squared. So this means that this algorithm, which by the way uses Monte Carlo and matrix product state methods, it is going to beat the quantum algorithm with an exponential advantage in n for any fixed m. Right, so basically we've boxed in the quantum algorithm now, because we have Schrodinger, which is good for large m at fixed n, and we have BGM, which is good for large n at fixed m. And so we've boxed in the quantum algorithm. So clearly already from here, asymptotically speaking, there can be no quantum advantage for sufficiently large m and n. However, this is a little too fast because we haven't talked about memory. And the Schrodinger algorithm requires storage of all 2 to the n amplitudes. And that's infeasible for n greater than about 50. And BGM has a different problem. You see that the scaling with the circuit depth is very poor. Right? So it has a huge prefactor, which makes it, in practice, not a practical algorithm. So we need alternatives, and those are essentially tensor network methods, which we just heard about. So one tensor network method, which can be analyzed in full, essentially, is known as the Schrodinger Findman algorithm. And this algorithm, it's a trade-off between width and depth in order to reduce classical resources. So what it does is it subdivides the circuit into p patches, each of which is simulated to full fidelity. So imagine a small patch that you can just brute force solve using Schrodinger. And then you need to connect the patches using Findman paths. Each patch that you simulate to full fidelity costs time and memory that scales like 2 to the n over p. The runtime scaling is a complicated expression, but what's nice about the Schrodinger Findman is that you can actually write down this expression and analyze it. So I won't explain it in any detail. I'll just say that the components here are this p times 2 to the n over p is the cost of simulating p patches exactly. Right? And then once you're done, you need to compute the partial amplitudes of 1 over f squared bit strings, but no more than 2 to the n. So that's where this comes from. And so that's the pure patch simulation cost in parentheses, and the other factor here is the cost of running the Findman paths between patches. Okay, so the point here, this scales essentially like m times root 2 to the m times root n. with everything else also known. And more general tensor network algorithms, there are many variants and many different authors, and I just picked one. I apologize for leaving out many others. But they basically all scale like m, 2 to the order m times root n, just like Schrodinger Findman. All right, so these methods are good for, trade-off between m and n, let's just say. Okay, so now that we've seen a number of algorithms, and by no means an exhaustive list, and by the way, I should comment that you don't have to simulate the circuit. You can also try to do something completely different, to spoof the XEB metric, and that's been discussed as well. Maybe you can bypass simulation and just try to directly go for the XEB quantity. I won't go into that, but that's another way that you can derive a classical boundary. Anyway, focusing on the simulation algorithms, they all scale exponentially in either the width or the depth or in both. And that is also true for the quantum hardware algorithm. So because we're comparing an exponential quantum runtime to an exponential classical runtime, at most we can expect a relative polynomial classical advantage or quantum advantage. And so it makes sense to introduce this polynomial scaling exponent, alpha sub c, such that this is the definition of this exponent. And by definition, if alpha sub c is positive, we have a polynomial quantum advantage. And if alpha is negative, we have a polynomial classical advantage. I hope that's obvious from this expression. And so C here denotes the Schrodinger algorithm, the Schrodinger Findman, or anything else you'd like, any classical algorithm. Now, we should also account for the actual clock speed constants if we're going to make a complete comparison. So the total runtime is the t from the previous slide multiplied by the clock time. And that could be either the clock time associated with the Sycamore chip or that associated with running things on Summit or any other classical computer. The actual numbers that we used in our analysis came from Sycamore and from Summit. All right, so with all that said, now let me present the results. And so here's what we find, and I'll present this in several stages. So what you're seeing here on the left is the result of the Schrodinger algorithm versus the quantum runtime scaling. And the y-axis is the circuit width. This is the circuit depth, or number of cycles rather. And the color denotes the values of this alpha exponent from the previous slide, right? Which, remember, positive alpha gives us a polynomial quantum advantage. Negative means there's a polynomial classical or Schrodinger algorithm advantage. And the first thing to notice is that as you increase the circuit depth or the number of cycles, indeed there is a transition from a quantum advantage to a classical advantage, and the transition happens along this red boundary. So alpha is positive on the left, alpha is negative on the right. The data that came from Google's circuits, well, actually the circuit sizes, those are these green dots here. So remember, they did circuits of fixed size, a fixed number of cycles 14, varying the size, and then at fixed number of qubits n, varying the number of cycles. So that's all the circuits that they ran. So these all live within the quantum advantage regime, except that if we take into account the actual clock speeds, then this red line bends, And you see that, and the reason it bends is simply because the classical clock speed is much higher than the quantum clock speed. So it actually helps the classical algorithm to take that into account. And you see that some of these circuits are now excluded. Only points above the dashed black line are within the quantum advantage regime now. So this is what happens for the Schrodinger algorithm, which is very good as a function of depth. The Schrodinger Findman algorithm generates this diagram, and now the boundary line has moved to here, and so circuits that are too wide become classically give a classical advantage. And if we combine the two, and by the way, I have the black dashed lines here as well when we account for the runtime. So if we combine Schrodinger and Schrodinger Findman, we get the hatched region here. And this hatched region is where there remains a quantum advantage. And everything outside of the hatched region, circuits that are either too deep or too wide, they no longer exhibit a quantum advantage. Now, very interestingly, the Google data is within the hatched region. So they pick their circuit sizes very well. Okay, this is not the whole story though, because what I didn't mention, I want to point out now, is that this analysis ignores classical memory constraints. So essentially here I allowed, for example, the Schrodinger algorithm to actually store those 2 to the n amplitudes, which is not feasible. So we have to do a little better, and also account for classical memory constraints, which will impose some additional constraints on the classical advantage. But I also want to take into account 2 other important things. One is the quantum runtimes. So how long does it actually take? The Google experiment took 200 seconds. What if it had to take 200 years, right? Then that would be a different story. And I also want to account for the constant improvement in error rates of quantum technology. And of course, that's going to help expand the quantum advantage regime. So this is what happens when we account for the classical memory constraint. We no longer have an island-shaped boundary. We now have this. You'll remember this from the first slide I presented. Just for Schrodinger and Schrodinger Findman, shown here, and also tensor networks is the 1 point in blue here. So we see a region of a Schrodinger Findman advantage. That's the orange area. A region green of Schrodinger advantage. And the Google circuits, shown again now as red dots, protrude into the white zone, which is the zone where there is a quantum advantage. The largest circuit that they simulated is this extreme point over here, which took 200 seconds. Had they wanted to simulate a larger circuit, well, then this is the 1-day boundary, and this is the 100-year boundary. And the reason that it goes up so quickly in time is precisely because the fidelity decays exponentially, as we saw. So again, the choice, the design choice of these circuits was good. They lie within the region of quantum advantage, at least relative to the Schrodinger and the Schrodinger Findman and tensor network simulation. So far, it's possible that better classical algorithms will be discovered or optimized, and that the classical advantage region will grow, but that hasn't happened yet. You might ask, what happens as you change the assumptions about the error rate? All right, so this plot was generated with the actual isolated 2-qubit gate error rate that was reported by Google of 0.36%. So what if we were to reduce that error rate and worked with circuits of depth or number of cycles m that goes like square root width? That's what's shown here is the width. That's n. And so this is for circuits that generate enough entanglement to entangle any qubit, any pair of qubits, when m goes like root n. And you see how the quantum runtime scales in that case. Okay, but let's look at what happens if we were to rewind the clock and take us back a few years when the error rates were not 0.36%, but 1%. So that's just a factor of 2.8 larger than the current Sycamore error rate. Under that scenario, there would have been no quantum supremacy demonstration. Right, so you see here how the red dots are overtaken by the Schrodinger Findman algorithm at the largest circuit width. So it was a good decision to wait a couple of years until error rates came down to as low as they were here. This is what enabled the quantum supremacy demonstration. How about the future? So in the inset here, what we did was we took reported data on 2-qubit error rates, which are the red dots, and from a variety of different papers on transmons and related qubit types. And we just extrapolated without any real justification, just for fun. And so in the year 2024, if everything continues at the same rate, we will be here in terms of error rates. And this corresponds to a 0.1% error rate. And at that point, it becomes possible to extend the quantum advantage much farther, as you see. So essentially, the region, the area of a quantum advantage grows, unsurprisingly, but it grows very fast as you reduce the error rates. So let me sum up. Quantum supremacy, unless you decrease the error rate, is not something that can just grow indefinitely. It's always a region in the width and depth plane, bounded by classical advantage. Decreasing the error rates, as is shown if you compare these 3 panels here, helps a lot. Right? It grows the area of quantum advantage exponentially. Interestingly, increasing the width, so going along the vertical axis, helps more than increasing the depth. And this suggests, if we may extrapolate from these results on random circuit sampling to other quantum algorithms, that shallow depth algorithms that require no quantum error correction will do well in the near future on NISQ devices, the noisy intermediate scale quantum devices. So shallow depth is the way to go, at least before the onset of quantum error correction. And finally, you saw that the error model I used was extremely naive. And I would be very interested in work on better error models that account for non-Markovian dynamics, for 1/f noise, and so on. Those are definitely needed to get tighter bounds and more accurate estimates. And the last talk by Jonathan Keeling was very interesting in that regard. Maybe these methods, open system tensor network methods, are a promising way to attack this problem. So with that, let me thank my co-authors, Alexander Zlokapa and Sergio Boisho. I'll point you again to our preprint, and thank you for your attention.
Thank you so much for a really nice talk. Just before we start the questions, we will also have a breakout room later if anyone wants to discuss more privately. So any questions? So in the early part of your talk, you mentioned that maybe this spectral statistics could be probed, or whatever connections you had with Tomasz Prozin's talk. Mm-hmm. Could you elaborate on that?
Well, okay, so there's a lot of quantum chaos theory that underlies the analysis of these random circuits. And so the Porter-Thomas distribution shows up all over the place in papers on this topic. I think there's not much I can say about it beyond that, except to say that measures of quantum chaos could probably be insightful in guiding us towards what are circuits that are, what are, for example, entanglement patterns that would be harder to simulate, more chaotic, I suppose, would be harder to simulate. Seems like a straightforward idea. And more generally, the tools of analyzing quantum chaos, in particular, there's very nice progress on simulating open system quantum chaos. These tools seem to be extremely relevant for this activity.
I see. Thanks. So Stephen has a question.
Yeah, can I ask about this large N behavior where you get a classically simulable region? Is this something that purely is constrained to random circuits, or is it something that you could also get in some more structured problems where at large N it's easier to sample?
I don't think we can make a general statement like that about large N. So yes, the results here are quite specific to random circuits. They're also quite specific to an exponential fidelity decay. The classical algorithms that I mentioned are not specific to random circuits. The Schrodinger algorithm, Schrodinger Findman algorithm, and so on, those are general purpose algorithms. They're not, you can apply them very generally. Right? So the scaling that they exhibit as a function of both the N and M parameters is generic and not specific to random circuits.
Okay, thanks.
Braden, please.
Yeah, hi. For the purposes of this talk, are all the tensor network methods using exact contraction with different contraction orders and contraction patterns, but with no compression of the tensors in the intermediate steps?
I have to decline to answer that because I'm actually not a tensor network expert. So I simply borrowed the scaling analysis that was done for tensor networks and used it to to do the analysis that we were interested in here. So I'm afraid I don't know. Okay.
I think it is the case, and maybe it'd be interesting to see how compression of the tensors, whether that can be done and give even more advantage to the classical simulation. Thanks.
Certainly. Yes, I mean, one observation I have is that when the tensor network community got wind of this, in very quick succession, papers appeared that reduced the time cost, which started at 10,000 years, down to, I think it went straight from years to weeks, and then in a matter of months, it went from weeks to days. So the more tricks you apply, I think this will continue to improve. Whether the 200-second barrier can be beat is a different question. At the same time, of course, we have this behavior of improving error rates, which gives a huge advantage to the quantum devices. So it's a horse race where every extra factor of 2 and lower error rates buys you a lot in terms of expanding the quantum advantage region. So we'll see if tensor network methods manage to catch up.
Maybe I can also ask another question. I asked in the talk already that this is really an experimental computational science experimental result that you can simulate this Google circuit in 3 days or so. What did they actually use to do that? What are the important ideas there?
In the 3-day simulation?
Yes.
So that is the work from the Chinese group, the Alibaba group. which I gave a reference to. It is a tensor network type approach, which all I can really say about it is that they understood the structure of the circuits very well, took advantage of that, and then applied a lot of optimization.
Okay, thanks.
Could I ask a question about your quantum error model?
Yeah.
It actually seemed to work pretty well and was somewhat intuitive. Do you have a sense of where the leading corrections to that model come from physically?
Yeah. So to me, this is the next question I'm personally very interested in working on. What is the right error model? And the main observation is that the fit to the blue data here as a function of n is okay, but not great. There seems to be some curvature here, so this indicates that it's actually not a simple exponential decay, but perhaps a super exponential decay. And it's not entirely clear to me where that effect would come from. I suspect that 1/f noise has a lot to do with it. So in other words, as you run these circuits for longer, as you make the circuits larger, you start to accumulate more perhaps fluctuators that are bistable fluctuators that generate telegraph noise that are buried in these circuits, which would contribute to a stronger signature of 1/f noise. So that's one speculation. But to generate a first principles error model that is based on the physics of these transmon qubits is a very interesting problem. There's of course a lot that's known about that already from the superconducting qubits literature, but it has not yet been done in order to try to explain data at this scale, and that's because it's extremely hard to solve the models at this scale. So again, I think these open system tensor network methods that we heard about, for example, in the last talk, could be a good way to do that. What else might explain this curvature here? I really am not too sure at this point.
Thank you.
There are no more questions. We would like to thank Daniel again for the very nice talk. Thanks.
Thank you.